All right, today we're going to pull back the curtain on one of the most powerful and honestly kind of magical tricks in all of computer science. It's the secret sauce that makes so much of our digital world feel, well, instantaneous. We're talking about hash tables.
I mean, really think about it for a second. When you look up a contact on your phone or search for a word in an online dictionary, the answer comes back in a flash. It's not like it's scanning through a list one by one. That would take forever. So how in the world does it do that? How does it pinpoint the one thing you need from a literal ocean of data? Well, that's the exact puzzle we're solving today. You know, the easiest way to wrap your head around this is to picture a magic library. In this library, you don't need a card catalog, you don't have to wander aimlessly through the aisles. The title of the book itself, through some kind of magic, tells you the exact shelf number. You just walk straight to it. No searching involved. That right there is the beautiful, simple idea behind a hash table. Okay, so here's our game plan. First, we'll dig into that core idea. You know, the magic library concept. Then we're going to peek behind the curtain to see the actual mechanism that makes it all work. We'll also have to talk about the one big problem they all run into, collisions, and look at the super clever ways engineers get around it. And finally, we'll tie it all back to the tech you use every single day. So, let's start with that big idea. The whole goal here is to make a huge shift in how we think. We want to go from slowly searching for data to instantly knowing exactly where it is.
The official definition, a hash table is a data structure that stores info in what we call key-value pairs. So, in our library analogy, the book's title is the key, and the book itself is the value. A hash table creates this direct link from that unique key straight to the data, the value that you're trying to find.
And this is where the magic really shines, the speed. I mean, look at this. If you're searching a simple list, you might have to look at every single item. We call that O of n time. A more organized structure, like a binary tree, is way faster. That's O of log n. But a hash table, its average search time is O of 1, or constant time. What does that mean? It means it takes pretty much the exact same amount of time to find one item out of a billion as it does to find one out of 10. It's practically instant.
So how is that insane O of 1 speed even possible? Let's get into the nitty-gritty, the actual magic spell that turns a key into a physical address.
The secret weapon is something called a hash function. This is the engine of the whole operation. It's a special, really cleverly designed algorithm. It takes your key, let's say your friend's name, and it mathematically mangles it and spits out a number. That number is the shelf number, or the index where all your friend's contact info is stored.
So, the whole thing boils down to this simple three-step process. You give it a key, like the word apple, the hash function does its thing, runs its calculation on that word, and out comes an index, a number, like say 42. The computer then goes directly to slot number 42 to find the definition of apple. It's direct access. No searching needed.
But of course, not just any old formula will work. A good hash function has to be lightning fast. It absolutely has to be deterministic, meaning the word apple will always spit out the index 42 every single time, no exceptions. And crucially, it needs to be really good at spreading the indexes out evenly, trying its absolute best to give every key its own unique spot. And as you're about to see, that last part is, well, it's everything.
And that brings us to the main conflict in our story. Because no matter how brilliant the hash function is, sometimes the magic trick fails. And we run into a problem that is pretty much inevitable.
So the big looming question is this. What happens when the hash function takes two completely different keys, say two different names, and it generates the exact same index number for both of them?
This event has a name. It's called a collision. It's like our magic library telling two different authors to put their brand new books on the exact same single spot on a shelf. You can't just stack them on top of each other. You need a system, a plan for what to do when this happens.
Let me give you a super simple example so you can see it in action. Imagine our hash function is just take a number and find the remainder when you divide by 10. Okay? So you give it the key 15, you get a remainder of 5. But what happens when you give it the key 25? You also get a remainder of 5. Uh-oh, that's a collision. They both want to be stored in slot number 5. So, what do we do?
This is where computer scientists had to get really creative. So let's look at the clever solutions they came up with. You can think of these as the strategies our magic librarians invented to deal with a shelf that suddenly got way too crowded.
There are two main ways to handle this. The first is called chaining. This is kind of like putting a little hook on the shelf. If multiple items are assigned to shelf 5, we just hang them all from the hook at that spot in a little list.
The other method is open addressing. With this one, if shelf 5 is already taken, we just look for the next open spot, maybe shelf 6 or 7, and we put the item there instead.
Now, as you might guess, each method has its pros and cons. Chaining is pretty simple, but if one of those lists gets really, really long, well, finding something in that list starts to feel like a slow search all over again, which kind of defeats the whole purpose. Open addressing, on the other hand, is better with memory, but it can cause this problem called clustering, where filled slots start to clump together, forcing you to search longer and longer for an empty space.
Okay, this all might seem a little bit in the weeds, but let's pull back and connect it to your world. Because this simple idea, key hash function value, is, and I am not exaggerating, one of the foundations of our digital lives.
Seriously, where are hash tables? They're literally everywhere. They're what make database queries so fast. They power the caching systems that make your favorite websites load in the blink of an eye. If you've ever used a dictionary in Python, yep, you've used a hash table. They even play a huge role in storing your passwords securely by hashing them before they're ever saved.
So how do we keep these things running at top speed? Well, programmers keep an eye on something called the load factor, which is just a fancy way of saying how full is the table. Once it gets too full, maybe around 70%, the system automatically hits pause and does a rehash. It builds a brand new, bigger table and recalculates the perfect spot for every single item. It's like moving the library to a bigger building to make sure there's always plenty of shelf space.
And that quote really nails the entire philosophy here. The goal is always to keep adding, removing, and finding our data as close to that magical, instant O1 speed as we can possibly get. All those clever tricks for handling collisions, they're all just to serve that one beautiful goal.
So if you remember one thing, let it be this. Hash tables make a really important trade-off. They give up on keeping data neatly sorted, and they might use a little extra memory to keep things from getting too crowded. But what do we get in return? An enormous, game-changing gain in pure speed.
And that leaves us with one final thought. This elegant, simple data structure is working tirelessly behind the scenes in almost everything you do online. So the next time an app on your phone responds instantly, just take a second and ask yourself, without the magic of hash tables, just how painfully, frustratingly slow would our digital world actually be?